Linearly dependent vectors. In this diagram here, we show vectors A, B and C. And you can see that vector C is obtained by adding vectors A and B. Now, because C is a combination of vectors A and B, in other words, just the summation of those vectors, these vectors are what we call linearly dependent. You could note, by the way, that we don't have to limit ourselves to consideration of A plus B equals C. We could say C plus negative B would lead to vector A. So they are, in various ways, linearly dependent. I also want to point out at this stage that all we need is a combination of vectors, including scalar products of those vectors, to satisfy the property of linear dependence. That is to say, if I was to double the magnitude of A, this one here, if I was to double it to, 6, 4, I would be able to say that half A plus B equals C. Algebraically, we can represent this idea in the following line. If there are two scalars, m and n, that when used for vectors A and B lead to vector C, then we have linear dependence. Now, that means all we need to do is solve a pair of simultaneous equations to establish whether or not these vectors are linearly dependent. So, how do we do that? Well, let's just do it. We can form simultaneous equations in the following way. 3 lots of m plus n equals 4. And 2 lots of m plus 3 lots of n equals 5. I'm calling the first equation, equation 1, and the second one, equation 2. Okay, now we need to solve for m and n where possible. Well, let's do that. I am going to do that by multiplying equation 1 by 3. So 1 is getting multiplied by 3. So I end up with 9m plus 3n equals 4 times 3 is 12. I'm labelling that equation 1b because it is a scalar multiple of equation 1. Equation 2 I haven't touched. So it's 2m plus 3n equals 5. And now all I need to do is solve for m and n. So we can see that by subtracting equation 2 from 1b, 1b from 2 I should say, we get 9m takes 2m is 7m plus 0 equals 7. So m equals 1. And by substituting m equals 1 into the equation of your choice, probably equation 1, you'll also find that n is equal to 1, which is not surprising. These vectors, vector C is just made up of a direct addition of A and B, so we would expect in any event for m and n to equal 1. They have not. This vector has not been multiplied or divided by some sort of scalar. What works in 2D will work in 3D with an additional twist. So I've got 3 vectors here in 3D, A, B and C, and I want to know whether they are linearly dependent or not. We're going to start off the same way. We're going to set up, we're going to ask whether some scalar m times vector A plus n times vector B can equal vector C. And we start off by considering the first 2 rows of each vector, and we solve the simultaneous equation as in the previous example. Press pause and work your way through the solution here, where you'll see that m is going to equal negative 24 on 7, whereas n will equal 23 on 7. So if you're not convinced of that, just press pause and resume when ready. So we have the two solutions, m equals negative 24 on 7 and n equals 23 on 7. What we need to do now is ask ourselves, does that satisfy the equation formed out of the third row, which is 3m plus 8n, will that equal 22 if m is equal to negative 24 on 7 and n equals 23 on 7? Well, that's just a simple substitution, and we will conclude that when we substitute m and n in, we will get 16, which of course doesn't equal 22, so we may conclude that the vectors are linearly independent.